about edge dislocation in crystal. Edge dislocation is an imperfection structure in crystal that help material to stretch or bend without breaking. An edge dislocation happens when extra half plane of atom is inserted into the crystal. This creates an edge where the atoms are either compressed or stretched. Think of a stack of books. If you push one book into a stack, that creates an extra pressure on one side and tension on other side. That's similar to what happened with edge dislocation. When stress is applied to the material, this extra plane of atom is moved, causing the material to deform. The movement of edge dislocation happens in a way this is perpendicular to the dislocation line. In short, edge dislocation are imperfections that make material more flexible and help them deform under stress. Thank you.
Hi everyone! Today let's talk about a screw dislocation, a key concept in material science. It plays an important role on how materials behave under stress. A screw dislocation happens when part of a crystal is twisted due to shear stress. Unlike edge dislocation, where an extra plane of atom is inserted, a screw dislocation forms a spiral or helical pattern around the central line. Just imagine a stack of paper. If you twist the top while holding the bottom part still, it will form a spiral shape, right? It is similar on how atoms are arranged in screw dislocation. The movement of screw dislocation is slightly different from edge dislocation. That's all.
And now I will talk about stacking faults. Stacking faults is also a very common planar defect. It happens when the arrangement of atomic layers are arranged incorrectly. There are two types of stacking faults: intrinsic and extrinsic stacking faults. Intrinsic, where there is a missing atomic layer, and extrinsic stacking faults, where there's an extra atomic layer. Stacking faults usually caused by dislocation movement, growth defects, deformation, and high temperature. Although it is a planar defect, stacking faults also has some importance in engineering. One, it influences how the material deforms. It is also a very good semiconductor, and it also plays a very important role in annealing and creep resistance. Scientists also use TEM, transmission electron microscopy, and XRD, X-ray diffraction, to identify and detect stacking faults in crystals.
Alright, for part me, I will talk about twin boundary of planar defect. So what is twin boundary? Twin boundary is a type of planar defect where two crystal regions are mirror image of each other. For your information, there are two types of twin boundary, which are mechanical twins and annealing twins. Let's talk about these two types. So mechanical twins form due to stress or deformation, while annealing twins form due to heating or cooling. We already know what is twin boundary and what is type of twin boundary. So now I will explain about the importance of this boundary. There are few importance of this twin boundary. The first one is to improve mechanical strength by blocking dislocation. The second one is to enhance ductility, which is the flexibility of the material. The last one is to influence electrical and optical properties. So now I will give 3 examples of twin boundary in everyday life that can be seen in natural phenomena or man-made material. So the first one is ice crystal in snowflake. The microscopic structure of snowflakes show repeating patterns with specific symmetry, where twin boundaries form when crystal layer grow in different direction but remain in symmetrically related. The second one is metal hardened through mechanical processing. In material like copper or stainless steel, twin boundary form during cold working or compression, causing the strengthening the material without significantly reducing ductility. So the last one is plastic under high stress. Some polymer that undergo hardening or stretching can develop twin bond structure. So they can enhancing their durability and flexibility. So that's all for twin boundary.